No link?
Now it's ready.
Now it's
Can we
ready.
take this?
Perfect. Huh?
I think 3 copies, maybe.
Oh, if you want. Yeah, I
Of
can
the
also-
PDF. Of the PDF. All right. Good morning, everyone. Dames and heren, ladies and gentlemen, dear colleagues, I hereby formally open this session and welcome you all to the public defense of Sven Kiefer. Sven Kiefer has presented to the faculty the PhD thesis on the topic of cloud formation in 3D exoplanet atmospheres, in partial fulfillment of the requirement for obtaining the degree of PhD in science, astronomy, and astrophysics. Sven Kiefer shall now publicly defend his PhD thesis. You are invited to give a Sven, you are invited to give a presentation of about 45 minutes about your work, and afterward we will have questions. I will first introduce the member of the jury. So Professor Leen Dessin from KU Leuven, supervisor of the thesis, Christian Helling, who should be online, from the Austria Academy of Science, co-supervisor or main supervisor on the Austria side, Ludmila Carone, also from the Austria Academy of Science, co-supervisor, Patrick Wagner, who cannot be here, was supposed to be the chair, but he's sick and he apologized for not being here. I will replace him as the chair of the session. So I am Denis Defrère, I work at KU Leuven here, professor. Hans-Gert Everts from TU Graz, Austria. Kostup Hakim from KU Leuven. And Paul Palmer from the University of Edinburgh. Sven, please, you have 45 minutes.
Okay. It's fine, you can just mute it. Ah, yeah, mute. Yes, beautiful. Okay. Perfect. Yeah, thank you very much for the introduction. And I would also like to welcome you all from my side. Yes, second here. Where I'm now finally able to present to you the work that I've been conducting over the past 4 years. And hopefully, by the end, have you all convinced about the importance of studying clouds in other planets. So as you can already see, my thesis, cloud formation in 3D exoplanets, and we will go basically through that. And first, I'm going to tell you a little bit more about cloud formation, but then also about exoplanets and their climate. Before I start, I would like to thank, of course, my supervisors, Leen, Christiane, and Ludmila, and also David Gobrecht, who have all supervised me throughout those 4 years and really helped me along the way. I would also, of course, like to thank all my collaborators, because there have been many of them, and it was absolutely lovely working with all of you, and you all helped for the success that I can now present you today. And of course, I would also like to thank my examiners and the chair, who unfortunately cannot be here today. Good. With that, okay, it's working, great. Let me give you a quick overview of what I'm going to show you today. So first, I'm going to talk about exoplanets and their atmospheres, so that everyone here has the basics that you need to understand the work that I have been conducting. After that, I go into the 3 main research questions that I addressed, where the first one is clouds and their environment, where we have a closer look at how clouds interact and are affected by the environment that they're in. The next part will be the optical properties of cloud particles, where we will look at how light interacts with clouds. And as you will later see, there's importance because of many different factors. And lastly, I will be able to present to you the work that we did on the climate of warm Saturns, where we had a closer look at one specific planet, HAT6b, which has been part of my PhD journey, just as many of my supervisors were, constantly throughout. And it was a lot of fun working on it. And it's, yeah, you will see it in the end. I am very happy of the modeling that we were able to do for that. And then in the end, I will give you a summary of the work. Good. With that, let's dive into the first topic of exoplanets and their atmospheres. But before we leave the solar system, let's take one quick moment and think about where we can find clouds. Now, unfortunately, this room is a little bit darkened, but I'm sure that no Belgium ever has a problem to figure out that Earth is one of the most important planets where we can find clouds. You're all experts on that. And again, I love those images because you can already see the complexity of clouds in their atmospheres. And if that not already makes you want to study them in more detail, I'll hope at least this presentation can convince you. But it's not just Earth. Out of the 8 to 9 planets in our solar system, 7 of those actually have clouds in one form or another. So you can see them here. We have Earth, Jupiter, Venus, Mars, Neptune, Uranus, and Saturn. And all of those have clouds. Now there's Mercury, and if you want, you can also count Pluto, who do not have a substantial atmosphere and thus do not have clouds in them as well. So no matter your opinion on Pluto or not, it will not be that important for what you hear today. Now, if we go further out and we actually go to exoplanets, if we leave our solar system, we are encountered with a large diversity of planets that we can see. Planets that that are similar to what we know from our solar system, but also some that are vastly different. And one specific type of planet that I want to introduce you is our hot Jupiters. Hot Jupiters are planets with the radius and mass of Jupiter, but they are on an orbit that is much closer than Mercury. So we have these giant planets which are very, very close to their host star. So that means, of course, they're also strongly irradiated. They have temperatures which range in the thousands of kelvins. They have orbits on the order of days. And because they are so big and so close to the star, they are very suitable targets to observe. So we can learn a lot by studying them. Now, one additional feature that those planets have is because they are so close to the host star, they're tidally locked, meaning that always the same side of the planet faces the star, which results in a permanent day and in a permanent night side. And as we will later see in the third part of the presentation, this becomes very important once we look at their climate. Good. But now that we have the big picture, now that we know clouds are there, clouds are in the climate, let's go all the way back and zoom in and look at the very, very small the formation of clouds. So the very small picture. Now, before we again go to other planets, let's start with Earth, the planet that we know best, and see how cloud formation works here. So on Earth, cloud formation starts with aerosols. So these are small particles that can originate from deserts, from forest fires, or man-made pollution, and they are brought up into the atmosphere. Once they reach a part of the atmosphere where water is supersaturated, it can condense on and form a cloud particle. Now, if this cloud particle continues to grow and grow, it becomes larger and it starts to feel the gravitational pull of Earth and fall down as rain. It then collects into rivers, lakes, and oceans and evaporates again, forming the water cycle as we know it on Earth. Now, this works perfectly fine if you have, again, a substantial atmosphere, if you have a ground surface where these aerosols can originate, but it doesn't really work for gaseous planets. Now, in gaseous planets, cloud formation can only happen within the gas phase. So everything must happen within there. So let me walk you through how we actually model that on a gaseous exoplanet. Now, before we start with the clouds, we first need to have a look at the gas phase. And we need to understand the gas phase chemistry that is going on within these planets. Now, we model the gas phase chemistry using kinetic chemistry, meaning we're actually considering the rate at which particles collide and conduct those reactions. Now, for the work that I did and the work that you're going to see in this presentation, we focused on the nitrogen, carbon, hydrogen, and oxygen chemistry within these planets. And in addition to that, we also considered titanium and silicates because they are important for cloud formation. In total, we have 69 species and 780 reactions. Now, if you compare that to other chemical kinetics network out there, this is a bit on the lower end. Other works have hundreds of species and thousands of reactions. But since we want to combine it with cloud formation, which is computationally intensive, this is the network that we chose for this work. Now, once we understand the gas phase chemistry, we need to form these aerosols. And the way we model it is using kinetic nucleation, where we go from molecules, which you can see here on the left, to larger clusters. And while the molecules collide and grow in size, again, here you can see TiO2 growing to a TiO2 7, meaning there's 7 TiO2 molecules stuck together, forming a larger cluster. And before it is in aerosols, there needs to be more. So we need 100, 150 of those molecules stuck together before it has a size where it can act as an aerosol, just like we saw it before. Once these aerosols are present, we can have then bulk grow. Because I've already showed you the hot Jupiters and they are much, much hotter, what actually forms in the hot Jupiters are not water clouds, but clouds made from minerals. So you can see some example here, for example, some silicates, magnesium silicates, or iron-bearing species. Now, all of those will be solid within those cloud particles. So just like here on Earth, those are solid minerals we can find in the ground. They, on those hot Jupiters, they form cloud particles, solid cloud particles. Now they can grow through in two different ways. The first is condensation, where you have the species already present in a gas phase, and it condenses, it settles onto the cloud particle. The other way, for example, to form forsterite, so Mg2Si4, which is a bit more complex, can happen through surface reactions. So when here the surfaces are used to facilitate those reactions, allowing for more complex reactions, just like a little example that you can see there. Now, once the cloud particle is grew large enough, just like on Earth, it will feel the gravitational pull, it will settle and fall deeper into the atmosphere of the planet, where it typically becomes hotter. Now, the hotter it gets, at one point, these materials will become again unstable and they will evaporate, which is the same process, the same processes that we saw before, now just working in reverse and basically dissolving or evaporating the cloud particle. And this process then transports the cloud-forming material from the top of the atmosphere further down. So to have a cycle, we need some form of replenishment, which brings it back up into the atmosphere. And this is the basic cloud formation cycle in gaseous planets. And this is also at the core of a lot of things that I've studied. And you will see that this becomes important throughout the talk later on. Perfect. But now that we all have the basics covered, we all understand how clouds form in gaseous planets. Let's go into the first topic, the first research question, which is clouds and their environment, how they affect each other, how they interact with each other. And the first point that I want to talk about is the importance of temperatures. Because all the clouds forming this environment always have a temperature. And in a gas, temperature basically describes the energy within the different particles, within the different gas particles. Now, this energy can be distributed in different ways. You can see here the example of water, and there's basically 9 degrees of freedom that water has. So 3 of them are the vibrations that you can see here, 3 of them are rotations, and the last 3 that are not shown here are the movements, or the velocity of the particle in the 3 dimensions. And if we're in thermal equilibrium, all 9 of those modes have the same amount of energy. Now, why is that important? I just have you here a little animation of how you can see how water can, for example, cluster. And you can already imagine that this process strongly depends on how much energy there is within the particle. So the more energy, the more likely they are to break apart again. So we are very much interested in the temperature on how clusters can form. There was recently a very interesting study by Plain and Robertson, who looked exactly at those the energies within those different modes and the temperatures. So what you can see here in the plot is on the left, just focus on the red part for now. On left, you can see the temperature, in that case, the effective internal temperature. And on the x-axis, you can see different densities, where on the left, we're in a low density environment. On the right, we're in a high density environment. And you can already see if you're in high density, both the dotted line, which represents the kinetic velocity, or the velocity temperatures, or the velocity of the movement, the energy within the movement, and the energy within the internal modes, so the 6 that you saw before, is the same. But if you go to lower density environment, this can actually be different. So there we can have a different kinetic velocity and internal velocity, which, because of the reasons that I showed you before, can be significant for the formation of larger clusters. Now, this difference in temperatures has also been observed. Now, what we did during my PhD is we had a closer look at the impact of these temperature imbalances for kinetic nucleation, so the process that I showed you before. And what you can see here on the plot is on the y-axis the number density of particles, so how many of these TiO2 clusters there are, in this specific case with size 10, so 10 TiO2 clusters stuck together. Now, the very bottom, the dark blue bottom line, shows you the case in thermal equilibrium. So if all 9 of the modes have the same amount of energy. However, if we introduce now a thermal non-equilibrium, so a change in temperature, and in this case we cool the kinetic temperature, you can see an increase in the numbers of particles. And I quickly want to highlight here the significance. So we have here from the bottom to the top line, so from the dark blue to the bright orange one, we have a difference of 35 Kelvin, which is a very, very small temperature difference. But that already causes a change in the number densities of these cloud particles by over 2 orders of magnitude. So as you see here, if the clusters move slower, we can form more larger clusters. Now, we also did it the other way around, and we found that if clusters move faster, then fewer clusters form. Now, I want to stress again, this is what we also would expect in thermal equilibrium, but if you're in thermal non-equilibrium, even small temperatures differences become much more significant than they would in thermal equilibrium. Good. Now, going from temperatures, let's make a jump to the second way how cloud particles can interact with the environment, and that is through the chemistry. So here we had a closer look at how clouds affect the chemistry and vice versa. And what you can see here on the plot is first just the gas phase. So on the left, you can see now the relative abundances. So how much, you can imagine it as like how much percentage of the atmosphere is made from these particular materials. And we start by just letting it evolve for a long time until we reach chemical equilibrium on the left. And then we basically start the simulation. And since everything is already in equilibrium here, if we add our kinetic rates, it doesn't really change anything because we are already in chemical equilibrium. Now, it starts to become interesting once we add cloud formation. So let's add the first step. So let's just add nucleation for now, and specifically TiO2 nucleation. And what you can see might not be unexpected. So we have one species here, TiO2, who gets lower in abundance, and that is TiO2 because it now forms the cloud particles. And the values that you can see here is the gas phase only. So since now the TiO2 goes into the cloud particles, they're no longer considered in this graph. So we see a small depletion of TiO2 in the gas phase once we add nucleation. Now, really interesting, it starts to become when we add bulk growth, because then it looks like this. And now there's a lot of changes, so let me quickly walk you through the ones that you should actually pay attention to. So the first one, and a rather obvious one, is the depletion of cloud-forming elements. So we have here magnesium, silicate, and titanium species. And all of those are directly involved in the formation of clouds. And as you can see, for example, TiO2 here, before it was slightly depleted, now more, and that is because it can now nucleate and grow at the same time, which also means they compete for the material. So the more bulk growth you have, the less material you have for nucleation. Now, this, you can also see that SiO2 and magnesium also gets lowered in abundance because that is now in the cloud particle. The second thing you can see is the depletion of oxygen. So if you look, you can see on the very top, the blue line, water, gets slightly depleted, and the CO2 line, the orange or the red one, also gets slightly depleted. Now, in our model, because we're again in this very hot planets, water and CO2 are not the species that actually form clouds. So they are not involved in the cloud formation directly. But what happens is that a lot of the materials that do form clouds are oxygen bearing. And they remove parts of the oxygen from the atmosphere, and you can see this impact on other species that carry oxygen. Now, this leaves us with one change that I have not discussed so far, and that is what happens to CH4. Because you can see there a significant drop in CH4 once we added cloud formation to the gas phase. And we cannot explain this the same as magnesium or silicate because CH4 is not forming clouds. And it also is very hard to explain like with something like the oxygen depletion because CH4 doesn't really have oxygen in there. So that led us to a very interesting goose chase where we went deep into the network, and what we discovered was an SiO-SiO2 cycle. So if you're familiar with chemical notation, now look to the left, it will be more apparent there. If you have no idea what's going on there, just look to the right. This is the same thing, just as an illustration. So the cycle starts with SiO in the gas phase condensing onto the cloud particle. So we have SiO going from gaseous growing onto the cloud particle. Now, if there's molecular hydrogen around, it can cause a surface reaction where SiO evaporates into SiH and H2O. Now, this SiH and H2O with a little bit of more water can then react again. React again on the surface, forming SiO2 now. So that's not SiO, that's SiO2, different material. And in this reaction, it also releases molecular and atomic hydrogen. Now, parts of the molecular hydrogen can then be used again to react with the SiO2 and produces gaseous SiO again. And this forms this cycle. And you can basically go around and around. And now if you squint long enough at this circle, you will realize that the net reaction of one turn is molecular hydrogen that gets dissociated into atomic hydrogen. So H2 goes into 2H if you do one full rotation of this circle. Now, why is that important for a CH4? Because of those four reactions. Because you can see here how CH4 uses this additional source of atomic hydrogen to now go into CH3. CH3 goes into CH2, into CH, and then the CH is stored into H2CO. So through this chain of reaction, we're removing CH4 from the atmosphere and storing it in H2CO. And this is very important because CH4 is often studied within the atmosphere as a tracer of other processes that are going on. So knowing a precise abundance of CH4 is very important for understanding the atmospheres of exoplanets. And this cycle can affect the abundance of CH4 and thus become very relevant within these atmospheres if we really want to understand what's going on there. Now, we studied the impact this cycle has on CH4 for different temperatures and pressures. So on the y-axis, you can just see a measure of how much CH4 is affected, going from less to more. And you can see we did this over a range of temperatures and a range of pressures. The red X shows the point where the simulation was that I showed you before, where you saw the drop in CH4. And in this plot, you can immediately see that it becomes the cycle becomes more important for low density environments. So if you go to lower pressures, and you can also see that the effect peaks roughly around 1,100 to 1,500, a little bit depending on the pressure that you're at. Good. With that, I hope to have convinced you about the importance of considering the effect of clouds on the environment, but also the environment on the clouds. I have shown you how the formation of larger clusters can be impacted by temperature differences, how clouds deplete the gas phase of cloud-forming elements and oxygen, and how the surface of cloud particles can be the cause of catalytic cycles that further impact the atmospheres where clouds form in. Lastly, I want to stress again that both effects that I've showed you, the temperature as well as the catalytic cycle, are more important in low pressure environments. So if you go to high pressure, high density, high temperature environments, their equilibrium assumptions are more suitable and those effects become less important. Perfect. With that, I would like to go to the next chapter. Here, we looked at another form of interaction, this time with cloud particles and light. And for that, we needed to study the optical properties of cloud particles. Now, first, I want to reiterate, we're talking about hot Jupiters, hot planets, where the clouds are solid particles. And as you can see here at the example for the interstellar dust particle, which is a real image taken, those particles can be quite complex. Now, in exoplanet atmospheres, as we talked before, the clouds are also made of solid materials, and they can also be made of multiple materials at the same time. Not just like here on Earth, where we basically have water clouds, they can be made of different materials, making the properties of these particles fairly complex. So while we would love to study something as complex as you can see here and really understand it, right now, this is not really possible with our observations. So let's simplify the picture a bit. So how we can describe these mixed particles, we have basically different possibilities how we can describe them. And the first one is well-mixed particles. You can imagine this a little bit like granite, where all the different materials that make up the cloud particle material are mixed and woven into each other. So just keep this picture of granite in mind when we talked about well-mixed particles. Now, other approximations that we can make is, for example, the core shell model, where we have one species in the middle and another one forming a shell around this species. Now, this works quite well with, for example, the nucleation that I showed you before, where you have one species nucleating, another one growing a shell around it. But you need to be aware that this is also an approximation because multiple species can grow at the same time, and also the nucleating species can further grow on top. So while this is also, while it fits the cloud formation model, it is also an approximation. And then we can make further, even stronger approximation where, for example, if you look at batches, we assume that the different materials within a cloud particle just forms little islands. And so each material is basically just like a ball and they're all stuck to each other, which again is a simplification, but a way how we can describe it and how we can work with it. Then lastly, what is also often done is it is assumed that all cloud particles form single particles. So all of them form individual particles. Now, again, from the formation model that I just showed you, we know that this is not correct. For a lot of species, this will not happen that way. But it is a way that we can describe it in more complex model and more computational intensive model. So for the purposes here, we also include it so that we have a direct comparison of how it works in comparison to the others. Good. Now, I have the pleasure to introduce you to one of my favorite plots that I had during my PhD. Now, it's a bit complicated, but I will walk you through it, and I really hope you will all follow me, because then in the end, you will also see why this is such an amazing plot, and we can see so much from it. Now, let's do it step by step. So the first thing I want you to focus on the left side of the plot. You can see there's colors in the background, and the colors basically show us how much light can be absorbed. So this is the property of the cloud particle, how much light a cloud particle can absorb, or a material, let's put it that way. The bright spot here is where more light is absorbed, and the dark spot, for example, on the bottom right, shows areas where less light is absorbed. Now, within that, we can now study how mixed materials behave. And here we take one very specific example. We take a cloud particle that is made from two materials, and that is forsterite, which you can see on the bottom, Mg2SiO4, and iron, which you can see at the bottom. So the black dots mark points where we have just iron or just forsterite. And the two lines that connect those are ways how we can calculate the opacities if they're mixed. So if we have a percentage of iron and a percentage of forsterite. And the red one is called LLL, the purple one is called Bruckmann, and those are just two different ways to describe the optical properties of the same particle. And you can already see they differ. But if you go along the path, it basically shows us different percentages of mixing. So that's how we follow the paths. Now, on the right plot, you can see basically the same thing, just plotted differently. Where on the x-axis, we go from purely iron to purely forsterite with all the different mixings in between. And on the y-axis, we go from less light being absorbed to more light being absorbed. Okay, now that was a bit much, but now we have all the basics to show you why this is such a cool plot. Because here we look at the example of how the particles interact with light at 7 micron. Now, 7 micron is a wavelength of light. If you don't know what it is, just imagine it as a color of light, a very specific one. Now, you can already see here one very strange thing. So LLL and Bruckmann are two ways to describe the same particle. So in theory, they should result in the same thing, but they are derived using different approximations. And you can see that this has a significant impact because the two peaks you can see are, first of all, at different places, and they have a different height in the peak. So we can already see that the assumptions made within the derivation of those two techniques are important for the properties. Now, luckily, this is not all we can learn from this plot, because if we go to a different wavelength or a different color, in this case 1 micron, we can see another really cool properties of these mixed particles. Where I want to focus on the right side, because there you can see it very nicely. If we have a purely iron or a purely forsterite particle on this dotted line, it absorbs less light than a mixed particle. And this shows us that mixed particles are not just a combination of the individual ones, but they have actually more complex properties. And you can see a little bit why on the left side, where if you follow the curve, it goes closer to this maxima, which is why it peaks more. Now, the last thing we can see is if we go to 10 microns, another wavelength. And I want you to remember this wavelength because I will mention it 2 more times during the talk, and this will relate to what you see right now. Because if you go to 10 microns, and if you look at a purely forsterite particle, you can see on the right side of the plot that it has a very, very high absorption efficiency. And that is because 10 micron corresponds to a specific wavelength where forsterite can absorb a lot of light. So this is a property of the forsterite particle. Now, if we mix just a little bit of iron in there, you can see that it sharply drops, and we basically lose this very strong absorption very quickly once we have mixed particles. So this is another way how mixed particles can affect the optical properties of cloud particles. Now that we know how the optical properties works and have all convinced you about the importance of looking at this in detail, let's take a step back and look at how we actually observe this in other planets. Now, this is one of my favorite images. It's a sunset, and I hope some of you already have a little bit of question in the faces, like this does not look like a normal sunset, which is true because it is not a sunset on Earth, it is a sunset on Mars. Because sunsets on Earth are typically a little bit more reddish. And the difference, why they look so different, is of their atmosphere. But because they have a different atmosphere, and when light passes through those atmospheres, it will be affected differently. And if we now take one step further back, so now we're standing there, we're looking at the sun at the sunset, but we go further back, further out, we at one point will see this. So we're now way, way beyond. Before that, we were standing on this little black ball. We were looking at the sun during sunset, enjoying our time, and now we're a bit further behind. Because this is actually how we can detect and characterize planets. We can imagine that this is now a star further out, and if the planet goes in front, we can measure the dip in brightness. So what you can see here is on the y-axis the brightness of the star. So if we measure the brightness, and depending on the position of the planet, we can see a dip if the planet is in front. So if the planet is on the side of the planet, it is brighter. Once it goes in front, the star becomes darker because we now see less of the star. Now the atmosphere around it will let through a bit of light. So it is not like the black circle blocks out all the light. The transparent part around it blocks parts of it. So if we now look again in different colors or in different wavelengths, this might be blue, but maybe another wavelength will absorb less light. Just as we've seen before, one sunset is blue, the other one is red. So depending on the colors, there might be more or less, the lights of different colors might be more or less affected, and red might absorb more light. So then we see, more of the light gets blocked. And now if we take this very same idea, we can put this into a scientific plot, which looks like that. But don't worry, it's basically exactly the same thing. So we already know what this is. So if you look on the y-axis, this is the measure of, this is a proxy for how much light is blocked. So if you are on the bottom of the y-axis, that means there's very little light blocked. And if you go up, that means there's more light being blocked. And the x-axis just donates different wavelengths, or as I said before, different colors of the light. And here we can really see why it matters to understand the shape, the morphology, the structure of those cloud particles. Because if you look around 4 micron here, you can see all these different lines represent the same atmosphere, but calculated assuming different properties of the cloud particles. So different, the assumption that I showed in the beginning, from well-mixed to individual to core shell particles. And you can see that if we assume that cloud particles form well mixed, they absorb more light. And if you assume that they are core shell, they absorb less light. So depending on what is actually true, we will observe something different within the atmosphere. Now, what is even cooler is if we go at 10 micron, remember, second time that I mentioned it now, where we see these peaks. And these peaks correspond to this property of forsterite. And core shell, as well as single and batch particles, keep these properties of these individual particles, whereas well-mixed particles lose it. So there you can see these more broad spectral features for both Bruggemann as well as LLL. Good, perfect. With that, I hope for the second time now, have you convinced that knowing the optical properties of cloud particles is very important, because if they're non-mixed, we now have shown that they can keep the individual properties of the cloud particle materials. If they're well mixed, they have new, complex, and typically broad features. And I've also shown you that the assumptions that we make on the calculation of these particles matter because they will have observational differences. And lastly, I hinted at it before, is that especially iron-bearing materials and carbon are very important cloud particle materials, because even small inclusions of them at some percentage can dominate the properties of the cloud particles. Perfect. Now that we know how clouds interact with their environment and how they interact with their light, it is time to put it all to a test, so that we actually look at the climate of a specific planet, of a warm Saturn. Before we go there, just 1 second of a break and admiring again this picture, because I think it just shows clearer than anything else the importance of understanding clouds, but also understanding the three-dimensionality of clouds, so the distribution that they have over the planet. We can see this already here, and it becomes even more, or it becomes similar is true if you go to exoplanets. I don't want to pit one against the other. Before we go to the planet, just quickly, why are they so important? And of course, there's many reasons, but if you look at the climate, there's two effects that you need to be especially aware of. Because if we have clouds in the atmosphere and we have sunlight coming in, they can actually reflect part of the sunlight, causing less sunlight to reach deeper layers of the atmosphere. At the same time, if we have thermal radiation from the planet itself, it can also be blocked back. Now, if we take the example of Earth again, and we go to Seoul, this was last week, and we look at Thursday, which was a cloudless day, and then on Friday, they had clouds, you can see exactly the effect of those two. So first, if you follow the yellow line, you can see that during the day, it became colder when the clouds appeared, because they reflected some of the sunlight and caused less light to reach the ground. At the same time, the nights became warmer, because now more of the heat from the ground could be kept around. So we see both of those effects very clearly here in this example for Seoul. Now that we know how clouds can affect the climate, in this case the weather, we also need to be aware very quickly that clouds are also, of course, important for observations. We've seen this before with transit, but we now know that they are not just annoying observers because they can't see anything in the telescopes. They're actually also very important for our understanding of the atmospheres. Good. With that, let's go to my friend, the warm Saturn HAT6b. First of all, warm Saturn, I introduced to you hot Jupiters, but I assume you can guess what roughly a warm Saturn then is. So warm just means it is not as hot as a hot Jupiter. In this case, we're talking about 700 Kelvin, which is around 430 degrees Celsius. It has roughly the mass of Saturn, but it has at the same time the radius of Jupiter, so it's a bit more puffed up, which is very favorable for observation. Now, the star that this planet is circling is HAT6b, which is an M-dwarf, which are known to be very active. So there's a lot of stellar radiation and stellar energetic particle, which in fact affects the environments. They're also small, which means that HAT6b has a very favorable transit depth. This example, 3.2%, which is one of the largest transits we know, which makes observations again favorable. And lastly, HAT6b is temperate with an effective temperature of around 700 Kelvin, as I mentioned, which means before we even did simulations, we expected that there is a lot of cloud coverage on this planet. Now let's go to the simulations that we conducted. Before I show you the results, just quickly explain what you're going to see. This is an isobaric map here at roughly 1 bar for Earth, and all the plots that you will see, you can imagine like this. So it's just the whole globe just stretched into a 2D map. Now remember, those planets are tidally locked, so the part of the atmosphere that points towards the sun is always the same. In this case, it's exactly smack in the middle of this plot. Put this to the side, we keep this in mind, and now let's see what we did. So to model the climate of HAT6b, we used a global circulation model, a GCM, which models the temperatures and the winds. So we run that first cloudless, so there's no clouds in there yet. Once we ran the model, we extracted one-dimensional profiles all around the globe and calculated the cloud structure, which we then put back into the next GCM run. And this is how it looks like. So in color in the back, you can see the temperature, and you can immediately see that there's differences. So that there doesn't need to be much closer investigation. We can see they're different. So that's already good. The second thing, which you can see less clearly in this plot, is that also the winds around the equator became faster. So the clouds affect the temperatures, which then affects the winds. And so we have all these effects that depend on each other. Now, of course, if we now have a different temperature structure, that means the clouds are also going to be different. So we again calculated the clouds and then again ran the GCM. So this is how it looks after the next iteration between those two models. And to be sure, we did it 3 more times. Okay. I don't think you can. It's a bit. Yes. I'm not entirely sure where I can turn down the lights because this is hardly. Yeah, this is very difficult to see for the audience here. Oh, perfect. Oh, okay, I see. Perfect. Thank you very much. Okay, now that we can see the plots better, because otherwise I was just going to say, you can see small difference in this plot, and with the light here, you would not have been able to see them, which is the second point that I wanted to make. So we can see that going from cloudless to cloudy, there is a clear difference, and there are small differences between the different cloudy plots. So we know we have roughly in the same regime, but there's still differences. To have a little bit of a better look at it, let's look at the height profile, so the vertical component. And for that, we zoom in on the substellar point, which is marked here as a red dot, which gives us this plot. So here you can see the temperature for different heights. So on the left, if you go very up on the y-axis, that means we are high up in the atmosphere at low pressures. And if you go further down, we are further down in the atmosphere at higher pressures, and we see the temperatures. Now the gray line shows us the cloudless one, and all the colored one shows us the cloudy simulations. And you can see, again, directly the differences. And you can also see that there's small differences between the cloudy models, but they're not that extreme. And also the differences, if you think back, can also be explained by an effect that we saw before, namely the yellow one. Because now that we have clouds, they block light further up in the atmosphere and don't let it penetrate so deep. So that's why we see the cooling deeper down in the atmosphere, where the colored lines are below the gray one. And further up in the atmosphere, where the light actually gets absorbed, it now becomes hotter, and it is hotter than the gray, the cloudless line. Now, I already told you, we still see some differences within these models. But the question we then ask ourselves, do they matter? Will we be able to observe them? And for that, we look again at transmission spectra. So just like before, on the y-axis, you can see how much light gets absorbed, and on the x-axis, the different colors or the different wavelengths. And if you go from iteration 0, the cloudless one, to iteration 1 with clouds, you can see clear differences. Very, very clear. We don't need to discuss that. But when we go further between the clouds, you will see less. So what we actually looked at is the differences between the transits, so the absolute differences between those transit spectra. And we compare them to the spectral accuracy of JWST. So here we have two different cases. The gray one shows a more realistic case where we have two transits. This is if you write a proposal for JWST, what is more realistic that will actually get through. The other one requires 10 transits, which is a lot of time, which is a bit idealistic, and you probably need a good friend in the committee selecting your proposal to get this one through. Or you need to be very, very convinced about your sign case. But it is just a bit idealistic. So now if we look going from iteration 1 to 2, I need you to look very closely and not blink, because otherwise you're not going to believe that there's something has happened. Because on the top one, there's not really anything happening. You can see they're basically overlapping. Now, if you look at the bottom, at the differences, we can also see that they especially focus on the right part from 1 micron further down, which shows us the difference in the cloud top. So there's basically this line shows us how much the clouds shift. You can see that this is already at the spectral precision of a very idealistic case. Oh yeah, I forgot to mention, we want to be below the black and the gray curve. So below is good. Now if you go from 2 to 3, it looks very similar. If we go from 3 to 4, we now see a shift slightly above. Still below the gray one, but now slightly above the black one. But if we go from 4 to 5, we can now see here in the red line on the very, with 1 micron or below, so on the very left, we are now a bit like, yeah, below the spectral accuracy of an idealistic case. And only in the middle of the plot, you can see some of the lines going above. This is because of the chemistry, small changes in the chemistry. But since we were mainly iterating between the clouds and the climate, we were focusing on that. And we were happy once we saw that this change at least is around the precision that we'll not be able to observe. Now, let's have a look at the spectra itself. So we take the top spectra of the last iteration and look at it a bit closer. So this is the purple line you can see in the middle. Then you can see the colored mountains, like those bumps. Those represents the contribution to the spectra of different molecular species. And in black, the black line that goes horizontally is the contribution of the clouds. So now if we zoom in, for example, here, we can see that the green bump is CH4, and CH4 is above the black line of the clouds you can see further below. So we see, okay, it peaks above the clouds, and we can actually observe it. For me, actually more interesting is if we go around 10 micron, because here we can see a bump of the clouds. And this is the third time that I now mentioned this 10 micron, because here we have, again, this bump, which is caused by these silicates. And if you look closely in the background there, it's white. So if there would be no clouds, we would expect a dip. If there's clouds but no silicate, we would expect a straight line or straight-ish. And because of the silicate, we have this bump. So with this, we can actually investigate the clouds in these atmospheres. And with that, I would like to conclude what you just saw. I showed you the iterative model between clouds and climate, which allowed us to execute both in their full complexity. I showed you how the clouds cause a temperature inversion and the cooling in the lower atmosphere and where it's coming from. And I also explained to you briefly that the winds are also affected, mainly they're at the equator become faster. And lastly, I showed you that even though this is a cloudy planet, which might hide a lot of stuff, we are still hopeful to detect CH4 and maybe even silicate cloud features. And with that, I would already like to come to my summary, where I quickly go over to what I showed you. So if you have not paid attention for now, pay attention now, because this is what I hope you will all take home. So first of all, clouds are affected and affect their environment. They're intrinsically coupled to it, and we cannot ignore them. They have a strong impact on their environments. The second thing is that the optical properties of cloud particles can be complex, but they also foster a lot of possibilities to look deeper into the exoplanets, their atmospheres, and allow us to learn more. And lastly, that clouds do affect the climate, here in the very specific case of a warm Saturn, HOT6b, and that we hopefully will get at some point observations, which can also help us then further understand these planets. Yes, and with that, I would like to thank you all for your attention, and I'm happy to take any and all questions. Oh, yes. I think it just might take a moment. Oh, okay. Yes, it should turn green in a second.
All right. Okay, thank you, Sven. We'll start the question from the examination committee by Professor Paul Palmer from the University of Edinburgh.
Dear candidate, let me be the first of the examination committee to congratulate you on such a scholarly piece of work. It was extremely useful, wonderful piece of work. I really enjoyed reading it, and I think it demonstrates the importance of these atmospheres, the importance of the atmospheres on exoplanets, and what we can and what we can't learn right now. I appreciate the fact that you've also illustrated the importance of the Earth in your presentation. I think that's, as you know, I study the Earth. I think sometimes we forget this is also a planet that needs our attention right now. So I have some questions for you. They're mainly limited to Chapter 5 and Chapter 6. So Chapter 5, your cloud opacity calculations, you need information about constituent quantities. Now, I was just curious, how certain are you about the information, the data that underpins those opacity calculations? Presumably they are derived from laboratory-based measurements. So I'm just curious whether you think there's enough information in the community right now. Is there perhaps some degenerate, I mean, there's some limitations. I'm going to give you a few questions anyway, so you're going to have to remember this. There are also some you've limited your calculations to a few components. How much degeneracy is there in these calculations that you've been doing? So there's two things. One, do we have enough information from laboratory-based measurements? Two, how much degeneracy is there in the calculations you're doing?
No, this is an absolute excellent question. Thank you very much for that. And you're of course absolutely right. So a lot of the data that we're using have been derived from laboratory measurements, and a lot of that is also quite old. So a lot of our sources are definitely from the 20th century, and they were also taken from various sources. So there's not one comprehensive piece of work where you can find all the different opacities, and we had to look them up in many different places. Luckily, I personally didn't have to do that. This was already done previously in the research group that I've been in, since they looked already at the optical properties of cloud particles. But one interesting case, which I think highlights, is that there's Casio3, I think, or Casio3, I need to look it up, which we do not have data for. So we actually had, this is one case where we discussed this a little bit more in detail, because we tried to look through the literature and we couldn't find any reliable source for the opacities for this specific material. And that brings me to your second question, like how much are they degenerate and how much are they different? Because if you look at materials with similar compositions, so for example, magnesium or silicate-bearing species or silicon-oxygen bonds, you will find similar properties between them. But still, typically, if you want to look at it in very much detail, you need to have this specific molecule, because you saw, for example, the peaks in forsterite, and we were confident enough to tell that this is forsterite because exactly of the position. And of course, we investigated a little bit further by removing the other materials and seeing that they're still there. But this specific peak at which it happens is not really a property of other materials that are similar to the ones that we have. So while you can use similar materials, if data is completely missing, I would encourage, I hope we have a lot of people online watching that do laboratory experiments, because I really want to encourage you to look again at the properties of these materials. Also, please do that in temperature ranges that we encounter in hot Jupiters. So if you have an oven that can go to thousands of Kelvin and you can do measurements in there, I would be very happy, so that we can also prove that they work on those environments as well. But you're right, they are done from laboratory measurements, and of course they suffer from uncertainties that are natural to those experiments.
Thank you. So you showed the results from using different cloud formation models, and you're making assumptions about the structure of the internally mixed, externally mixed particles. The difference in transmission you get using those different models, do you, and given uncertainties associated with the data that we have right now, do you think you have sufficient information to determine which model best fits data?
I think it is, I think it is complicated, and I agree with that. It is certainly possible to get an idea about it, but you're right that investigating into very much detail is, for example, I showed two effects. One is the different muting, and one are the spectral features. So the different types of muting are very difficult to disentangle with other degeneracies, like the number of cloud particles that can exist there, the height of the cloud particles, where exactly the clouds are located. So there's a lot of degeneracies in these measurements. On the other hand, the spectral features that we saw of forsterite and so on, so these very nice peaks, if we could observe something like that, that would be very helpful, because there's much less degeneracy in that. Now, it is not as one-fits-all solution, because again, other silicates have similar-ish features. So there has been 2 detections now of silicate features in exoplanets, and I think both of them discussed actually the mixing and how different materials might be discerned and might not. And while there is agreement that it is silicates, which silicate it is exactly, there's some strong evidence, but I wouldn't say that we can confidentially point at one and tell you it's that one. But we are now really at the verge of going there. So at the verge of having information to investigate it, to look deeper into it. And I really hope, by including this, the calculations that I have also in retrieval models would really help us to understand what can be distinguished and what cannot be distinguished.
Great, thank you. I was particularly intrigued with your core shell model. As you know, there is a similar situation on Earth. I don't know if you're familiar with the semi-indirect effect of aerosols. So much of what you talked about is completely irrelevant to what we see on Earth. Does it matter which constituent is in the core and which is in the shell? And if yes, how does it affect your how would it affect your calculations?
Yes, it actually matters a lot. So you need to discern two different cases. One where you have a very big core and a very thin shell. And this is actually the case where it becomes most important, because there you have effects of the specific morphology of core shell. And this will differ significantly to the other particles. Whereas if you're in the case where you have a very small core and a very big shell, you're mostly dominated by the shell and you see very little input from the core that is in there. So it really depends in which case you are. And we also saw this with some of the exoplanet models, whereas if the core material starts to dominate, you get really different effects. Yeah, and I fully agree again for the importance for Earth. There's also knowing exactly which material again is in the core, how the shell forms around it, can then help you to discern the formation of those particles through optical analysis. So this, I know some papers who have done that, but again, as soon as you add reality to the mix and you don't have perfectly spherical cores, perfectly spherical shells, it becomes more tricky to really connect theory with models, but there have been attempts to do that.
Great, thank you. I've just got a couple more questions. They're both focused on your 3D modeling.
Yes.
You've used two models. You've used a 3D model for the atmospheric meteorology, effectively the dynamics of the planet, but then you've used an offline model for clouds and fed that into the 3D model.
Yes.
You've convincingly showed that there is some, there is, after some iterations, you get some kind of convergence in the state. I wonder whether you've looked at the patterns you've showed there. Are they stationary or is there some time dependency? I ask because some of the work we've been doing showed there's quite a lot of variation, particularly around the substellar point and the terminators, that could influence, some of the conclusions that you've shown.
No, that is absolutely true. So the iterative model again does not allow the clouds to immediately react to changes within the GCM. It does it on a bit of a longer time scale. But you're right that if you look between iterations, you can see variations, and also going through those those 6 different iterations, we always saw those differences. So it never looked like it converged to one perfect solution. And there's no changes anymore. And this, as you mentioned, can of course be because maybe we need to do more iterations, but I would not fully believe that, because then again, clouds are a dynamic part. They can heat the atmosphere. The heating can then reduce the cloud coverage. Reduce cloud coverage leads to less heating. This then again leads to more clouds. So you can kind of have these cycles that occur where cloud formation is just inherently dynamic, which is one of the reasons, honestly, why we also chose HAT6b, because we knew it had a global cloud coverage and we expected it to not be subject to catastrophic cycles of that. So where we go from fully cloudy to no cloudy at all. So we also, when we look at the cloud profiles, we see some differences between iterations, but they become less and less until they're still varying, but on a level, again, that is not observable.
Okay, good. This is my last question. You'll be relieved to know. There's a hypothesis well, it's not really a hypothesis you put forward, but the anti-greenhouse gas effect
Yes.
and testing that. So you've put forward, you have clouds that effectively warms the upper atmosphere above the cloud deck and it cools below it, and that forms an anti-greenhouse gas effect. Now, and Titan, you've cited as this as an example, but Titan also has a greenhouse gas effect. So this kind of, for me, emphasizes the importance of using 3D models, because you don't have such thick cloud decks everywhere on your planet. It will be some breaks there that could balance it out. Do you have a feeling, and it's a bit of an unfair question, but do you have a feeling for whether HAT6b, which one wins out? Is it the greenhouse gas effect or the anti-greenhouse gas effect, and whether you've looked at it at all?
Yeah, so I would like to answer this question in 2 parts, because you perfectly described a lot of what we investigated during our study of this planet. And the first is that clouds can have various different impacts. So you can have a greenhouse effect if they keep more heat. You can have an anti-greenhouse effect like on Titan if you refract more light. And which one of the two occur is really dependent on your atmospheric conditions and on the planet. And as you perfectly pointed out, 3D modeling, I also believe, is very crucial to get that correctly, to really understand which effect dominates and how effectively the clouds affect the atmosphere. Now with HOT6b, which is a planet where we look deeper, more exactly or more precisely at the climate, to the best of our models, to the best of the assumptions that we added there, if we, again, trust these assumptions that we make, the deeper in the atmosphere, this anti-greenhouse effect will dominate because we, again, absorb so much in the upper atmosphere and irradiate it from there again, so it can't really penetrate deeper. So for this planet, I would assume that, again, the anti-greenhouse effect is more important. There's also other studies of similar planets, for example, by Duncan Christie, who looked at the similar-ish planet, but they also saw a similar effect. Not exactly the same, because again, different planet, different atmosphere, different effect of the clouds, but they also saw a cooling of the lower atmospheres once the clouds remove heat from the upper atmosphere. So, short answer, it really depends. For HOT6b, it is this anti-greenhouse effect that dominates.
Okay, great. Thank you very much. That concludes my questions.
Okay.
All right. Next, we have Professor Hans-Gert Everts from TU Graz.
Good morning. I would like to congratulate you also on your very nice presentation. Thank you. I have a very simple question on that. You mentioned that in a gas planet, of course, the material that has fallen down needs to get back up, be replenished. What's the main mechanism for that?
Let me think. I think it depends a little bit again on the planet that you look at. Our models were originally developed for brown dwarfs, where it's convective overshoot. For the gas planets that we look at, we assume it's similar-ish effects where you have this convective mixing that brings up elements from the deeper atmosphere. But of course, if you look at it closer, you can also consider diffusive effects, which are also sometimes modeled in different cloud formation models.
Okay, thank you. Can you maybe go to page 23 of your presentation? Way back.
23. I can try. I gotta admit, my computer is slightly overburdened by this, but I will happily try to go there. Might take a small moment because I'm running the streaming service at the same time in the background, and it's not very happy about it.
Maybe if you go from the start and then up.
Yes, that might be a better way. And I think I can also just, if I go here and then directly to 23, that is indeed a better idea.
One before. Yes. Okay, maybe a little larger, can barely see it.
Yes, it is doing that.
Okay.
Not very efficiently. I can just zoom in here for the time being. It should open it full screen any moment.
Okay, fine.
Later. Yeah, I'm
now,
very sorry. My computer is stuck now.
These are logarithmic scales on both axes.
Yes.
And the time scale on the horizontal axis especially goes over really large, different scales. Two questions on that. Are these time scales practically relevant? That's the first question.
Yeah. So the timescales that you see here are not practically relevant. This is basically how we modeled it. So what we model here is we assume a box, and this box, the nucleation evolves in this box. And what you can see here is the difference until it reaches a static state. And this just takes a very, very, very long time. But we conducted similar simulations with some additional assumptions where this is more dynamic, where, for example, the cloud particles nucleate, and then they just basically we dissolved them and fed them back in the beginning, which simulates kind of a cloud formation cycle without all the details. And there the timescales become much shorter. We've seen this also in other works. For example, the there's one from Kuhn et al., who looked at a very similar study, also with like this box model. They found similar timescales. And then also other studies which do this kind of assume that the cloud particles grow, dissolve, and are replenished. And there we also then found much shorter timescales as well.
Now, in your calculations, how do you handle such different timescales?
This is a very good question. So one thing how we are able to handle this is that the time stepping of the ODE solver is chosen logarithmically. So we start with very small time steps, which we then slowly increase further and further. Now, if your system is very well behaved, this allows you to basically first get the small scale effects out of the way in great detail, and they'll do small time scale, and then get the large time scale effects. Now, this is such an interesting question because cloud formation actually prohibits that. Because once cloud formation sets in, you again have an effect that works on much smaller timescales, namely the bulk growth processes that set in, which then need you to again reduce the time stepping and go because you then need to resolve again this effect of the cloud formation until this is out of the way, and then you can do again larger time stepping.
Okay, thank you. Related, on several of the plots, you look at densities of different constituents, which are again very, very different. For example, the one where on the top you had the water density and then others below.
You mean that one here?
Beyond. Yeah, that one.
Yeah.
Yes. How do you take care of these large orders of magnitude change?
They were actually never really a problem. So we are using the DLS ODS solver for that, which again is a solver of very stiff differential equations. And at least this orders of magnitude that you can see here, while we check for the relative errors of each of the materials, usually works then perfectly fine. You are right, though, we do have some materials, and especially when we start in cloud formation, where we are several orders of magnitudes lower than that. So there we go to -30 at points. And there it can become a little bit tricky with the resolution. And also in that regime, I really cannot be confident about the results that we have. But luckily, because they are so low, the precision there doesn't really affect anything from the network. And we tested out different accuracies. So we went from more accurate, like enforcing more accurate calculations, which of course take longer, to a little bit more lenient ones. And we didn't see a huge change in the species that actually matters. So the ones at abundances that you can see are like 10 to -11 and larger, that we can actually, that have a larger impact.
So you don't have any problems with some species being at 10 to the -11 and changing there, and others at 10 to the -4 or 5 at the same time?
No, not really. At least from what how we tested the solver, how we investigated it. Again, using different accuracies, using different networks as well. We also tried to have different accuracies for different molecules, but that was not really required. So no, we didn't encounter a lot of problems. Again, for these scales that you can see here, if you go further than that, it becomes a problem at some point.
Okay, later in your talk, you emphasized that different models with different underlying assumptions, like LLL and Brüggemann, for example, produce quite different physical results or predictions.
Yes.
Is there any hope on improving both of them, really, so that eventually they agree of doing it differently?
Yeah, that is a beautiful question. So I am by far not the first to point out that they're different. So there's a lot of people, especially in solid state physics, who use them sometimes. They have done investigation, and they also find that they disagrees on the certain circumstances. However, no one could really, like, if you actually can compare it to laboratory measurement, there's not that one is better than the other. Sometimes one agrees better with the result, other times the other. And it's really a consequence of the way they were derived. Because what both theories try to do is they try to describe incredibly complex particles. and they just can never capture the full complexity of the particle, and thus they will always be wrong. And depending on which assumption that you make, you get closer to the truth, but it's even very hard to tell which one of those is better suited for the case that you're using. Which again, I would also love to have even much more in-depth and very detailed observation for planets, because then we can also start to figure out, okay, if we now know that they're well mixed, which theory describes it better, and then we can again compare it to solid state results, which we can then use to again learn more about how the cloud particles probably look. But the second problem is as well, I mean, I showed you granite as an example of how they could be well mixed. Granite is actually already a little bit too, like the particles within granite are already a little bit too big for what we're doing. They should be even smaller. But if you have a material like that, there's just very little theory that can explain it. One of them that tries it mostly tries to explain shape effects rather than the composition effect is the discrete dipole approximation, where they try to get like very complex shapes and how they interact. But that takes a lot of computational power and again, a lot of assumptions that we just don't know if they're true for an exoplanet. So we need better observations to limit what which we can investigate.
So for all your calculations, which involved a large number of different techniques with different assumptions, which one or two would you like to improve on the most? Which assumptions concern you the most?
Oh, that is a very good question. So let me think for a moment. So I think the one that concern me the most, that I think are most relevant to improve, is the connection between clouds and the climate. So the one that we showed in the end. Like, we chose this iterative model, which allowed us to really include the complexity of the cloud model. So we didn't need to make a lot of simplifying assumptions on that end, which was really helpful because we wanted to have the microphysics of the cloud formation and wanted to study that in detail. Other models have tried to include cloud formation fully into the GCM, like on the hydrodynamic time step, fully coupled to each other. And they just take forever to execute. It is so computationally expensive that they need to make assumptions on the simplifying the cloud model, which then again gets you the clouds wrong. And as I showed you before, it can be very crucial. If you make those simplifying assumptions, you just lose some of the effects that could otherwise occur. So I personally think it would be great if you find a way to make clouds in GCMs more computationally feasible. So we can either remove the assumption, again, this small time stepping, this long time stepping that we did, or a lot of the simplifying assumptions that I have to make on the cloud model, because that can then really tell, as Paul asked before, about this like dynamic effects that are happening within the atmosphere, which, as you've seen on Earth, are very relevant and cause our cloud structures.
You just mentioned better models need much more computer time, naturally.
Yes.
How much more do you think would really help? 1,000 times? Would that help?
The way I mentioned it before, I think what we need is, rather than having more computational time, I want to have more efficient numerical methods that can handle the models that we're doing. So we need to rely on less corrections, less assumptions. Increasing the computation time can help to some extent, but for example, for the GCM we looked at, if you want to run one model for one planet, you can add more and more cores, so you can parallelize it, but you can only parallelize it to a certain extent. And at that point, throwing more computational time at it, or more computation power specifically, will not really help you that much. So rather than just increasing the number of computational time that we had, in regard to the question you asked before, it would also be good to improve the numerical methods that we are having.
Okay, thank you very much.
Right, next we have Dr. Kostubakim from KU Leuven.
Yes.
Dear candidate, I was also very pleased to read your thesis, and I would like to say it started with a very theoretical chapter 3, and towards the end, it really went on to connect to observations. So, which is remarkable. In one thesis, you really go from basics of theory of nucleation to how can we observe something in a warm Saturn. Also, I appreciated that you had a introduction chapter for a generalist, which is not usually the case in thesis. So that's well done, I would say. Of course, I have many questions, and
Yes.
many I have asked before, but I'll keep it short today relatively. And first, I would like to ask again about the silicon monoxide dioxide cycle, which you discovered. So
Yes.
this time I would ask something else about it. So it's really a complex set of reactions
Yes.
which go on underplay in really depleting methane in this scenario. So there could be a lot of such reactions happening for different systems. So for example, for Venus, we know there has been recently discussion on sulfur cycle.
Yes.
So depletion in sulfur dioxide content in altitudes above 50 kilometers and so on. So could there be a generalized way to think about such cycles which can deplete certain molecules over others by forming clouds? So is there something you maybe have already thought, or maybe you think could be useful for modelers to discover?
Yes, very interesting question, and one that I have not thought about in that specific angle before. I mean, you're absolutely right. I love that you brought up the example of Venus, because they're looking at how cloud particles can affect the chemistry, and also using, in that case, if I remember correctly, the liquid cloud particles that they have for also similar issues, because now you have a liquid environment where we can also, not catalyze, but facilitate some other reactions that can take place. For cloud particles, as we've seen it, there is some general ideas that can be used. For example, like cloud particles acting as a catalyst, and also specifically for hydrogen, is not something new, because it has already been discovered in other places where in this case, the reverse pod, where the cloud particle can facilitate the recombination of hydrogen. Because hydrogen, just like the molecules, have the same problem. If they collide, form a hydrogen, they have a lot of remaining energy, so they tend to break apart again. But you can remove this excess energy with the cloud particle. And in the end, something very similar is also with the SiO2 cycle, where it now provides additional energy for the dissociation. So in this sense, yes, this is a general principle, and you can think about it in that way when looking at cloud particles, and also when you want to investigate new reactions or new possibilities how clouds can affect the gas phase. If you talk specifically about the SiO2 cycle, you're absolutely right. Those are quite complex reactions that use the surface and material that is already on the surface. Now, if you want to see if there's other similar reactions, you basically need to investigate a little bit more, like what kind of complex reaction can occur on those particles, how exactly do they occur, because we do make a lot of simplifying assumptions when we do those calculations of those rates. And by improving that, you hopefully will get even a more in-depth feeling of which complex reactions are more likely to occur and which one are less. And then again, to really figure out which one can cause such a cycle, because again, here are multiple reactions involved, you would need a comprehensive network to really figure that out. And then, study it in great detail over and over again. Yeah.
Okay, thanks. Then I have a question regarding your favorite plot.
Yes.
So you showed like a,
Okay, I will try to guess where it is.
55.
55, perfect. Okay. Yes, my computer is really not a fan for this double setup.
Yeah, it's there.
Okay.
Yeah. So here you discuss a two-component model between iron and forsterite.
Yes.
And of course, you show nicely with the different models, there are different ways you connect basically one end member to another end member material here. So of course, in reality, you already talk about this in the thesis, that clouds are much more complex. They are they have heterogeneous particles.
Yes.
So if you have more than two components,
yeah,
is there a way to deal with this, or would some approaches like, I don't know, machine learning could be useful in investigating this future? Because I also heard your answer to the previous question,
Yes.
that from the lab experiments as well, it's kind of difficult to choose whether we should prefer LLL or Bruggemann, for example. So this could be, I think it's a big challenge. I'm just thinking out loud what could help the community on this.
No, absolutely. So the thing is, why I specifically chose a two-component material here is because it allows such nice investigation. It allows you to plot very nicely on an XY graph and show it. Once you add more components, you can do exactly the same analysis. And the good thing is, this is not that computationally extensive. Like Bruggemann, a bit more. LLL is very, very quick. So computationally, you're not very limited here. It's really more your tools for analysis. So how you can actually study this multi-dimensional parameter space. Now for our application, specifically for the thing we studied here, it was less important, I would say, because we saw most of the effects that can happen already like very nicely with two-component material. And once we then, basically we then went to the next step where we already looked at realistic cases. Now, if you want to study the in-betweens a bit more, there of course exist, and I really like that you mentioned machine learning, because there is a lot of techniques in machine learning that are meant to also deal with this like a lot of parameter space. One that personally comes to my mind, because I worked a lot of it in my master thesis, would be principal component analysis, where you could look at, okay, if we have this parameter space, which are actually the materials or the changes that cause us the most. And what I personally would find interesting, do they align with materials? So for example, here, is it just if we add iron, there's more, or is it something like this effect in the middle where we can actually see that a certain combination of materials could cause more or less changes? Now again, for this study, we didn't really do that because first of all, we did a detailed analysis of the techniques using this material that we understand very well and where we can make clear conclusions. And then the next thing is we looked at specific planets where we tried to model those specific. And again, I am confident in the results that we have for the complex planets and for the analysis that we did in between. But you're right, of course, the middle step could also allow us more insights into the properties.
Okay, then it brings me to my final question. So you also briefly talked about this. James Webb's time is very competitive.
Yes.
And when you look at the published papers, all these papers use retrievals to figure out what kind of abundance is there. All these retrievals have forward models going in them.
Yes.
Of course, given the resolution of data, the forward models could be less or more complex.
Yes.
But given what you have seen in the last couple of years and given your work, what is one thing you would ask the modelers to take from your thesis into their forward models?
The good thing is the one thing I asked them is the one thing they already started to doing, which is please take clouds more seriously. Because at a lot of the time when you see them dealing with clouds, it is like, oh yeah, they just flattened the spectrum. So they just added a straight line into the plot. And as someone who actually looks more detail and how clouds affect and also studied what we can actually learn from them, it hurt my heart a little bit to see how much simplified it. But I think a lot of the people now realize that clouds are more complex and people now slowly start to add more and more complexity to their model. Now, of course, again, this is very, like the models we use here are very computationally extensive and it is unrealistic to do retrieval with them. But again, there's a very good middle ground where we can already start to include more and more. So for example, the mixed, like Bruggemann is a little bit of a bit complicated to calculate, but you can do it fast enough. LLL and the other one are so quick that you can easily take a model and then analyze the different ones. So you can just have multiple of the different morphologies and then do a retrieval on all of them and see if one of them fits better than the other, which would, for example, if you then study the features around 10 microns for silicates, if you get lucky, may or may not help you to discern them. But again, as I talked before, when I answered one of the questions before, I want to be carefully optimistic. There's definitely a lot we can learn. And whenever I see a new JWST paper that has like MIRI observations, I always check the 10 micron and see if there's new bumps. And a lot of them are very promising. But I think the more data we're getting, the more, the better we can do our analysis. And what I would really love, if I can hijack your question a little bit, if we can have a good JWST observation of like one object where we spend a lot of time to really, really get good error bars on these measurements. That would be very lovely, because more object is fine, but having one in great detail would also be help us a lot to understand the cloud formation. Yeah.
Thank you.
All right, next is myself, so Denis Defrère, professor at KU Leuven. First, I would like to congratulate you, both of you, on your manuscript and your presentation. I think this is really excellent work, and I really enjoy reading and following your presentation today. So I have a few questions. I already asked you a lot of questions before, but I have a few questions for today. So first, as you know, I'm doing direct imaging.
Yes.
And so I'm really curious about what you think about different things. The first question is about clouds. So we have also, we can detect clouds in direct imaging as well. And for you, can you elaborate on how clouds impact differently a transmission spectrum from an emission spectrum? Let's say I have a planet, I consider the same planet. How would cloud impact differently a transmission spectrum from an emission spectrum?
Yes. So first, I want to make a short disclaimer. I studied the transmission spectrum in great detail. I looked at the thermal emission from planets and how this will look like in a spectrum. But what you have is when you do transmission spectrum, you actually look at how much light from the star gets absorbed throughout the atmosphere. Now, if you look at an emission spectrum, depends a little bit which wavelengths you look at, but if you look at wavelengths where the planet emits, you basically, what you can do is you can look at the thermal radiation coming from the planets, penetrating through the atmosphere, and then does something very similar. Now, clouds become important here because clouds are, for all intended purposes, very opaque. So they are very much giving you a border. So it can also basically set where your emission comes from. So if they are higher up in the atmosphere, you will get basically the temperature of these clouds, because everything below that, your emission will come from the cloud deck, because everything below is just absorbed from the clouds. So this then can be, I assume, again, I didn't look too much into detail into that, but this can also then give you very interesting knowledge about like where exactly would your clouds be, because depending on that, you would have different temperatures of an emission. You would see different shapes of black body-ish of the emission that you see. So that is very different from looking at transmission spectra, where all it does is basically block the light from the star, which is already given by the star. And then, of course, you can also see a little bit from the height as well, but less direct than for the emission spectra. But looking through the clouds is, again, for emission, not really possible.
Okay. So you focus your work on one of the warm Saturns. Can you comment on the occurrence rate of this kind of planets? Do we know how frequent they are?
So I don't know the exact occurrence rate, but one of the things also why we studied Hot 6b, because it's a warm Saturn around an M dwarf. And I mentioned it very quickly that this raises some question about planet formation, because M dwarfs are very small stars. Or just the smallest stars that we know of, and then we have such a huge planet, and how can so much material form into a planet around such a small star? So in that cases, they are actually rather rare. And I think we looked at it, there's currently around 10-ish of those planets that we are aware of, which in the grand schemes of the thousands of planets that we are aware now are very rare. Now, if you go warm Saturn in general, you can, of course, also, they can exist around brighter stars. So more massive, more luminous stars, and basically just similar like to hot Jupiters, just be a bit smaller, a bit further out, and then you would get similar-ish temperatures, and you would also classify them as a warm Saturn. Of course, they will be different because they are now further out, their orbital period is longer, their rotation rate thus is a bit longer as well, and this will affect your climate. So it will not be the same as Hot 6b that we have. It will be a different case, but you would also classify it as a warm Saturn. Now, with those planets, again, with hot Jupiters, we know that they are, I don't know exactly when is the last time I checked, but I know that they're between like 0.5% to 1% in that area are the occurrence rate for hot Jupiters. And again, since warm Saturns are kind of like a sibling family of that, I would assume that your occurrence rate for those planets around more massive stars is roughly the same. But But again, I want to reiterate, around M dwarfs, about the small stars, it is way lower.
Okay, and I have a final question. So not counting existing instrument,
Yes.
what are for you the most promising research direction in instrument to learn more about exoplanet atmospheres?
Oh, this is a very interesting question, because I think one of the big advantages is using different techniques, different instruments at the same time. So of course, James Webb is amazing with the transmission spectra, but a lot of the high resolution data we get from ground-based observatories are also amazing. Like it probes different regimes in the atmospheres. We can learn different things. So I think in the end, if you would ask the question more neutral, I would say it's the power of all these techniques combined that we have that really makes the next step forward. I think what is most important, I would go for a very easy answer, because it's also where all the money goes. It is the Habitable World Observatory. It is LIFE. It is facilities that can really push down the boundaries of the size of the planet. Because as I mentioned before, the biggest planets are the easiest one to observe, but for the smaller ones, we're actually still very limited what insights we can get. And we are basically ignoring, we must neglect right now a lot of planets that we would love to study in much more detail. And those instruments are exactly the one that will allow us to push the boundaries to those and really solidify the picture that we have of exoplanets and the diversity. Because we've seen it times and times again, the more we understand the diversity, the more we understand, for example, the climate in different cases, the more we really understand what is going on in those planets and the more we can figure out. So I think this is the most important next step, to really push those boundaries and get to the smaller planets so they can really understand those as well.
Thank you. So next we have the supervisors and co-supervisors. We start with Ludmila Caron from the Austrian Academy of Science.
Good morning. Again, I join the other colleagues in congratulating you, Sven, for this amazing PhD journey. It has been a lot of work, but as you have shown, it was very worthwhile. I mean, extremely worthwhile. It has been a lot of results, and also great results that will help us to, push further with this highly exciting journey of trying to make sense of what cloud 2 and 3D climates of exoplanets. I have maybe a question which is a little bit out there. You mentioned that Pluto is something that is not of interest in terms of cloud formation. And I must admit, I was smiling a bit, because for Pluto, one of the great surprises has been, when you go there and actually look at the picture, that there are actually particles suspended above the surface. So can you maybe, do you have an idea what these are and how these are related to what you have done, or in how far they go beyond what you have done?
Mm-hmm. So I have not studied Pluto and the particles around Pluto. So I can give you the best information that I have based on the theory that I worked on other planets. So as we've seen, the cloud formation that I've showed, especially the nucleation and so on, those are all effects that need a substantial atmosphere, because otherwise the nucleation and also the bulk growth become very, very inefficient. So what I can imagine for Pluto is also something that works similar maybe to the haze formation on Titan as well, where you have other effects that can also then facilitate the formation of larger clusters. Now, I'm not entirely sure about the extent of Pluto's dust particle, but I would assume those are small particles. I would be surprised if there are really large cloud particles or dust particles around Pluto, which again would hint towards like a formation similar to haze formation on Titan.
Yeah, but could these, you mentioned nucleation, right?
Yes.
Which is the starting point of what you're doing. So could these planets inform you in some way?
Oh, sorry. Oh, yeah. Sure. I mean, if you have, again, if you understand if we go through the theory and we understand what the likely nucleation processes that happen on Pluto, it would of course be very interesting to study it, because you have it in an environment where it is probably more isolated than within an atmosphere where you have immediately bulk growth and other processes. So you would hopefully be able to study also more of a range of clusters of the formation process, and also how they actually grow. Again, here I'm becoming really unsure because it goes into territory that I have not studied in detail. But I would agree, like we've seen it times and times again, that if you know a process is happening in an environment that is very different than to the one that you studied, it typically allows you to to isolate some of the effects. Now, I would love to give you more details about what that could be for Pluto, but for that I would really need to go see the paper and read it a little bit more into detail.
No, perfectly fine. It is really just, you answered this perfectly fine. It's like exactly like, I mean, that's one of the things of a PhD, right? You become an expert in a thing, but you also have shown that you have also the capacity to, you know, look beyond the immediate topic that you have done. So that's very nice. Yeah, and that's for me. I'm very happy with the PhD journey, and also I'm very happy that finally we have come to an extremely successful end. And I would like to give now then the voice to some other member of the supervisor.
Okay, next we have Professor Christian Helling from the Austrian Academy of Science. You are muted.
Yeah.
First of all, thank you for giving me the the time to speak a little bit and come up with a question. But at very first, Sven, I would really like to congratulate you for this in-depth PhD work that has led us forward with respect to our modeling tools that we use to analyze and to understand extrasolar planets. I think without your work, we would have not come that far, apparently. But I also would like to congratulate you to the quality of the work you have conducted, the quality of the talk you have presented here and also in the internal defense, and also for daring to embark on this journey, which of course was not always easy because it is a PhD and it's not the bachelor, and it's not the master. It is a time where you really had to dare addressing fundamental physics questions, and where you, for the first time in your life, I think, have been given the chance to lead a rather diverse team of fellow students through a project which was by no means simple and straightforward. So therefore, again, congratulations and deep appreciations for the for the energy you have put into this, in all of this. I just have one question, which of course follows up on what I had just have said. You have demonstrated us the individual modeling tools you have developed and have used to lead us to new knowledge. Mm-hmm. And the most simple conclusion from this is the following, namely that in order to study extrasolar planets, we need to have the complexity of all of these models. So my question is now at the other end of this conclusion. If you were to have very limited resources, what would be your suggestion of how to model an extrasolar planet based on what you have learned through your PhD journey?
Okay, this is a very interesting question, which as you mentioned so far, usually it goes the other way around, where we try to really go into the details. I think what we have seen with the models that we use so far to understand the atmospheres of exoplanets is that oftentimes you can get a really good guess of what an atmosphere looks like if you consider the hallmarks of the properties. So for example, there has been done some very nice work on using machine learning and also disconstructed properties of exoplanets to model GCM, to get like the climate model very fast, very precisely. This was done by Jasmina Blecic, who did great work on trying to actually get this more efficient. And I think if I have very, very limited resources, I think I would go down this path. I would try to analyze, okay, which are the core properties of a planet that are important to get right for the thing that we want to investigate, and do this as good as I can, and then approximate the rest so that I get the dominant properties correctly of it. Again, I think the model of Yasmina shows this very well, that if you really want to get an idea of the climate, this does a beautiful job. But then if you want to know, really investigate the wind speeds at a particular location, you then need to have a more detailed model. So really, depending on the research question that you're asking, you should improve the quality of you should put the time that you have in the part that is actually most crucial to the model. And again, that depends on the question that you try to address.
How do you find out what the most crucial part actually is?
That I think is very different if you're an observer or a theorist. If you're an observer, you take the parts that have the most observable impact. If you're a theorist, like for example, in the chemical networks, you take the ones that have the most dominant effect on the species that you're interested in. So that is, for example, one of the reasons why we had a chemical kinetic networks that only had like tens of species and hundreds of reactions, because it was already reduced. It was already a point where you said like, okay, we cannot do the full modeling, but we focus on the things that are most important for the one that we are looking at.
Okay, thank you.
Okay, finally we have Professor Lindessin from KU Leuven.
Hi Sven, I also would like to join the congratulations already given by all of the other supervisors and by all of the other jury members. Also here realizing that this was a kind of a PhD where you're bridging for the first time the expertise of the other supervisor, Professor Helling, and what has happening here in Leuven. And therein the very important role also of Ludmila Caroni. So where we have started with the chemical kinetics here in Leuven, the cloud formation as expertise of Christiane, and then the dynamics, what is the expertise of Ludmila. I also would like to still ask you one more question, yes. And it's touching upon the question already asked by our colleague, Dr. Hakim, but also now by Christiane Helling, is on, you know, how do we actually know what are the chemical reactions that are the most important when you are talking about your SiO-Si2 cycle and the explanation of the methane depletion?
Yes.
You know, we are talking upon something that is out of equilibrium, a non-linear process. So have you then just been looking towards, let's say, somehow a way of determining the most dominant reaction rates? And are we then sure also that seconds or the reaction rates are also not the key for understanding what you're looking for? So maybe you can give us a bit more insight upon how you have been determining that cycle there.
Yeah. Absolutely. And I think it's a very important question, and it also hints at a very important just way of how to analyze all the, that goes into such a network and such a study. Now, luckily, like a lot of stuff, and as you already said, breaching the expertise also meant I was in a very fortunate position to use the expertise that I had in many different places. So for example, for the chemical kinetics network, there was already work done, different works in that case, which I could build upon. So people that already looked at the carbon, nitrogen, hydrogen and oxygen chemistry, where they already looked at partially also that, like how can we have an accurate description of that? There was also work being done on the cloud formation stuff, on the titanium and silicate chemistry. So I was able to really use that. But this is just the first step. This is, as you said, using what is there, combining it, but then it is also figuring out the importance. And while this was done throughout the project, I think the most interesting one that we did was actually together with a bachelor student, where we looked at the kinetic nucleation network. Because as you've seen in the image, clusters of all sizes can interact with each other. So a 2 cluster with a 7, an 8 with a 1, and so they can grow. And what we were interested is in exactly that, like how much of that does actually matter? Like how much of those reactions do we need to model accurately to get the same results as if we would do the full network, if we would consider everything. And in that case, it was a little bit more helpful because we knew the process as an isolated process, this nucleation, so we were able to isolate it a little bit more. And then we also find that you can make a lot of simplifications, which in a lot of cases still bring you the exact same result. He even managed to break it down to, I think, like 2-3 formation pathways that already gets you to 90-95% accuracy of what you're seeing. Again, not exactly the same, but very close. So really going then there and investigating that. Now for the SiO-2 cycle, this was a very particular case where when we first saw it, we saw the effect of it. So we looked at the data and we saw this depletion of methane, which, if I remember correctly, also was together with you when you looked at it and you were like, oh yes, this looks strange. Let's have a look at it. And then when digging deeper, this was actually one of the few cases where it could isolate it very well. So when you saw, I showed you the reactions that there were. I would love to bring it up, but I think my computer is slowly dying. We could really isolate it to those 4 surface reactions, those 4 gas phase reactions, and we were still be able to reproduce what we saw there. So we could really narrow it down to those reactions. But you're of course also right. This was specific for that case, and it could very well be that other similar cycles are much more complex. And then again, it takes a very close look to really first start broad, knowing that you're doing a good job at describing as much as you can, and then narrowing it down to the most dominant effects of a certain effect.
Good, thanks. Chairman?
All right, this is a public defense, so we have a few minutes for a question from the public.
First of all, congrats on a nice presentation. So you showed an iterative approach to add clouds to your modeling, which I think is logical. And then you compared the iterations to what we could see with JW. And when you were comparing between the iterations with clouds, what I took that to really be is, okay, we cannot yet see the weather on an exoplanet,
no,
essentially. What I would be interested in is, can we already distinguish between the different physics in those clouds with JW, like the different particle morphologies, for example?
Yes. So let me answer that in 2 parts. So first you said we cannot see the weather, which on its straight first surface, if you just state it like that, is true. So we see still very global properties. We're getting better at distinguishing them. But what, for example, I just want to quickly mention is that a lot of the cloud models now include something like a coverage factor. So how much of your atmosphere is actually covered. And some of them achieve the best result not at 100%, so like at 90%. So that can be, for example, if you have a planet like Earth, you will see some clouds and some parts are cloud-free, and that doesn't have to be static. That can also be dynamic. So in these cases, we might already have hints at something that is weather. But again, if you just take it at straight surface, I would say you're right. This is still very optimistic, not impossible, but optimistic. And the second thing you said, the observation of those morphologies, there's, as I talked before during the examiners, there's 2 parts. If you talk, for example, the muting, so the different levels that we see, this is going to be very hard, not particularly to observe, but to distinguish from other effects that there are. On the other hand, again, the peaks are better, are much, much better to use, because if you see clear peaks of a clear material, you know that there is not highly mixed materials there. It can be that there is either one material which shows the peaks is very much dominant and it's still a little bit mixed in there, but we already shown that small mixing can already destroy this. So it becomes less likely. And that would really give us a hint. Similarly, when we see broad features that we cannot explain with any single material, we get a hint that there probably must be mixed materials, because otherwise it's becoming very, very difficult to explain. So while it is still optimistic, it is definitely a very valuable avenue to have right now, where we're slowly going towards doing exactly that, where we have better observation and we're slowly going to figure out how can we use that best. Yeah.
Thank you.
Hi, Sven. So I'm Catherine. I'm one of the supervisors here in the network. I want to really congratulate you for the excellent presentation, but I also want to point out that you contributed really very extensively and enthusiastically to the education and art and science project of Chameleon. and that in very innovative ways. So you've contributed to role-playing games, theater productions about exoplanets. And my question concerns an initiative that you actually introduced in the network, which is
Yes.
MEME,
Yes.
the Massive Exoplanets meme exhibition.
Yes.
My question is, are you continuing with this? And what's the future for this very innovative way of doing science communication using humor?
Yes.
Thank you.
Thank you very much for this question. Yes, this has been a very interesting part of my journey. Both parts, as you said, connecting science way outside what we are typically considered to be like the constraint of our field. And I also quickly want to thank everyone who collaborated with me on that, because it was done in a much more, it was like really a collaboration and incorporation of what we did. Now to your question with the memes, yes, we are fully intending to continue that, because I think it is very important to communicate what we're doing. Because sometimes it can feel like you're looking at such a niche point, such a tiny, tiny topic that you're actually interested in. And you can imagine, like everyone in here who does science is probably aware that there's a lot more equations to what I've shown you here to the pretty pictures. And I think using different medias, using different outlets to actually share this information with other people can really spark interest. And once you have this interest, people naturally are curious and they continue. And we've seen this especially with the meme. So if you just give children something that looks funny, that is interesting, you already caught their attention, but much more importantly, their interest. So I very much intend to continue with that. And hopefully, again, being inspiring for others and also bringing the science that we are doing closer to the general public. Yeah.
Okay, we have time for a final quick question. If not, then the jury will now deliberate. We can connect to my Zoom link, and then we'll come back later.
Okay, thank you. Should be on.
Okay, so I will read the text from the faculty and the university. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation of the examination committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Sven Kiefer has presented to the faculty the PhD thesis on the topic cloud formation in 3D exoplanet atmospheres, in partial fulfillment of the requirement for the PhD in science, astronomy, and astrophysics. And Sven Kiefer has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulation have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Sven Kiefer the degree of Doctor in Science, Astronomy, and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALEA European Code of Conduct, reliability, honesty, respect, and accountability. I now close the session. Congratulations. To sign your
Just here. Oh,
here. And this one, and this is the same in Dutch. Okay.
Dear Sven, I first will congratulate you.
thank you very much.
Just a few words. You know, this has been a journey. Also, Katrien is here. I'm very happy that you can also join here online. You're one of our chameleon students, and this has been a journey for a lot of us, for you as PhD students, but also for the supervisors. On one hand, we were really daring to push you beyond boundaries, but also us as supervisors were pushed beyond boundaries. Pushed beyond boundaries in the way how you can collaborate if you have to start during COVID periods and you have to start collaborating with people that you have never met in person. That is challenging. And it also has learned us a lot upon how we potentially can do that, but also where we have failed. This is what science is. We fail not only when we do science, but also when you dare to do, when you try to collaborate, and when you at some point realizes that each of us has our own way of communicating. Each of us thinks that the other person is telling us something, but actually he or she was not doing that the way you're expecting that. On top of that, you know, you have dared to go and model something that I'm often using as if I try to explain to the public what is an emergent phenomenon. When you're explaining people, the audience, the broad audience, something upon emergency, they are often a bit puzzled since they are not used to that terminology. Yeah? You use that terminology when you say or try to say something of which you see what is happening, but you cannot explain it from basic principles. I often use the clouds. Sometimes I use birds or ants, you know, the behavior, how ants are behaving. Each of them is knowing what they should do, but they actually do not understand what the other ants are doing. Clouds are an emergent process. We see what is happening, but we do not understand the basic principles. And you have dared to do science on one of these most complex things, understanding emergency in physics. We are not yet there. The question is whether we once will be there, but at least you have shown us something. And this is, I'm quoting here one of my colleagues from the Netherlands, Henny Lamers, who was always saying, astrophysics, you know, is the physics of simple laws. And we can just say that things have an exponential behavior, have a linear behavior, have a quadratic behavior. This is his convention, his saying upon emergency. Emergency is something that in the end, and you have shown that at various slides, something seems to be very simple, but it's actually not true. But you have broken that principle of Henry Lammers. When you went through your thesis and through your various chapters, we have started seeing very simple emergent laws, simple laws. You know, you have exponentials and you have some quadratic laws, but the further you went through, the less we have seen this kind of a behavior. And this is since you are actually going into the depths and into the understanding and showing that astrophysics is not the physics of simple laws. Astrophysics is a physics of complexity. And now we are in that area where we can start tackling complexity. And you are sometimes very unsure upon how to do that. Tackling complexity in science, tackling complexity also in interaction with the people in a broad network. We are here, we have tried it, and you have shown us today that we can do that with success. And we are very proud upon what you have achieved, not only as a scientist in breaking the simple physical laws, but also as a person in trying to connect the people within that chameleon network in the way how you have communicated your science, as Catherine have been saying, in having these memes, trying to connect towards the audience, trying to engage young students, trying to engage the broader audience into the things we are doing. And so it's for this whole racing of things, all of these things that you have been doing. This is why you're here as a PhD now, as a doctor, as of today, and this is where we are proud of. Thanks a lot.
Thank you very much. Yeah. Thank you very much. Yes, I'm not sure. Do just me and then, or, okay, perfect. Well, yeah, thank you very much. Okay, now since my computer crashed, which is the theme apparently of my thesis, I need to guess on which slide I need to end, because I quickly wanna use my time. I know usually the saying goes when once once all the ceremony is over, I just have to say, and now there's a reception. But I am not a man of short words, so I quickly want to use this opportunity to say thanks again to everyone along the journey. First and foremost, I mentioned it before, I also want to say thanks to all the supervisors who have guided me along the way. As you said, there was a lot to it. There were a lot of things that need to be figured out, scientifically and otherwise. And yeah, I was very happy to embark on this journey, and I'm very happy, for all the things along the way. So thanks again to all of my supervisors. I really appreciate it. But there were so many more. So I want to also say thanks to the people at the IVS and the IWF who have been there for all of my journey, especially also to the IVS. This was during a pandemic. I remember my room very well because that's where I spent 90% of my time. But every time you managed to somehow get me out of there, even though it was a bit tricky with all of the rules and regulation, I very much appreciated it. And of course also the IWF. We did so much together. So it was, so much fun. I, of course, also want to thank everyone from the Chameleon Network. You were there from the beginning of the journey until the end. And it is such amazing how much that was motivating, how much we did together, how much we encouraged each other. So I really want to say thank you to all of you. It has been an amazing time. And lastly, of course, there always have been people in the background who supported me, who helped me, who encouraged me to really go beyond what I could already do. And I wanted to say thanks to everyone of those as well. Now with that, there will be more words, but I really don't want to be in the way of you and your food. And I also want to say thanks again to the people online, if they can still hear me, for joining in. And if you at any point or for any reason want to talk to me about my science or anything else, please always feel free to come to me. I always love to talk about it. Perfect. Then enjoy the food, and thank you to everyone again. Yes.